The first would be auxiliary heating units. These could be a hot water baseboard radiator located along the exterior wall of a space, or they could be a fan coil unit. Those two are just heat exchangers. They are expelling heat from the hot water loop directly into the air in the space. There would be a thermostat located somewhere in the space which controls the position of such a valve. Again, the term thermostat means that both the temperature sensor and associated controller are just housed together. In this case, the set point for the controller would just be the temperature you want your space to be at. The control variable would be the room temperature. The control device would be the two-way control valve, and the process plant would be the radiator.
Hey everyone, we're at another mechanical room here on the first floor of AFIT's Civil Engineer School. Here's another example of an auxiliary or terminal heating device. This is called a unit heater. Sometimes it's called a horizontal unit heater because the direction of airflow is horizontally across the coil inside of here. So in this device there's a hot water coil and there's also a fan. In this particular case we don't actually have a control valve. So if the hot water pump's running, it's going to be pushing hot water through here. But it's not going to be putting out too much heat unless the fan kicks on. So the fan is really the control device. And it's going to kick on if the space in here falls below some set point. Now, the set point can be adjusted over here at the controller. The controller and the sensor in this case are housed together. And what we said before is when you have a sensor and a controller housed together, that's a stat. So this would be an example of a thermostat. Thermostat with an adjustable dial for the set point. So if I turn up the set point, we would expect that fan to kick on and provide more heat to this space.
The third common location for a hot water heating coil in an HVAC system could be in what we call a variable air volume or VAV box. These are located in the ductwork right before the air gets dispensed into the space it is serving. The control loop, which operates a VAV box, can be a little complicated, as the VAV box has two moving pieces: a damper, which can modulate the amount of air flowing to a space, as well as this reheat coil, which can modulate how much hot water is flowing through the coil and subsequently how much heat is being added to the airstream. The complete sequence of operation for a VAV box will be discussed in a few lessons from now. But for the time being, let's just assume that it is winter, when heating is required. The VAV box controller will open and close this control valve in order to maintain the space temperature. So here's where the control loop differs a bit from that of the preheat coil. We are not concerned about the temperature of the air in the ductwork just downstream of the coil, as was the case back in the air handling unit for the preheat coil. In a reheat coil, the control variable is the space temperature, which is being sensed by the temperature sensor on the wall. I believe you'll be able to identify the rest of the components of the closed control loop, so I won't go there. But if you are unsure, pause the lesson and see if you can name them.
Okay, so we're in one of the classrooms here at AFIT Civil Engineer School. The temperature of the space is always being sensed or monitored. It's being sensed by that temperature sensor located over there on the wall. That sensed temperature is then being sent to the VAV box. And that VAV box has on it a digital controller which is comparing the sensed temperature to some set point. And based off of deviance from that set point, we're either going to send more or less hot water through this reheat coil, and you can see that reheat coil there. How much water is being sent through that reheat coil is going to be dependent on the position of the control valve. And again, that controller in the VAV box is going to dictate that position. That control valve can be seen on the copper pipe leading to that reheat coil. And the dead giveaway again there is the actuator, that orange box located there on that three-way control valve.
Okay, so we have talked about constant speed hydronic systems. We went through a few examples of how these systems are controlled and what occurs in the system as it experiences a variety of operating scenarios. We expanded a bit on this concept of pump curves and system curves, and we use them to better understand how these systems operate. The next lesson will take it a step further. We will provide the pumps with the capability to modulate their speed, and subsequently modulate the amount of flow they are pushing. Such a capability includes the introduction of an additional control loop. Again, the objective for this lesson was for students to comprehend the configuration, control, and operation of constant speed hydronic systems. The corresponding samples of behavior were: explain why 2 balancing valves are needed in a piping assembly serving a coil if a 3-way control valve is present. Describe why the term constant speed is more accurate than constant flow or constant volume when describing such systems. Summarize why 3-way control valves are far more prevalent in constant speed hydronic systems than 2-way control valves. Describe what happens to the system curve as 2-way and 3-way control valves modulate in a constant speed system. And identify the components of the closed control loop for common heat exchangers found throughout an HVAC system.